Alright, so I want to finish chapter 17. We got a couple problems left, and then we'll talk about capacitors briefly before we get into chapter 18. So this example is there's a piece of aluminum wire, so we're going to assume the wire cylindrical as long as it doesn't specify the dimensions. So just for now, if it says wire, we're just going to assume it's, shaped like a conventional wire. It's got a free charge density of 2.3 times 10 to the 27 electrons per cubic meter. So that's my lowercase n sub e. It's carrying a current of 5 amps. So my conventional current, my capital I, is 5 amps. We have a drift speed of 5 times 10 to the negative 5 meters per second. We're looking for the diameter of the wire, and if the wire is 15 meters long, what's the potential difference? So we have a lot of values given to us, which is nice, right? We've got lowercase n sub e, capital I, drift velocity, and the length of the wire. So we're looking for the diameter of the wire and the voltage across the wire. So first thing I'm going to do is find the diameter, right? So the first part is I have the drift speed, I've got the current, I've got the charge density. So I think this expression for my current is going to be handy because it's got the area in it. I know E, I know lowercase n sub e. So diameter's hiding in this area value right here. So again, I'm assuming that the wire is cylindrical, so I'm going to write the area as pi r squared, but the radius is half the diameter. So what I'm doing is I'm just substituting pi d squared over 4, right? So I'm squaring the diameter term, I'm squaring the 2, and I'm substituting that in for the area. So now I've got, once I substitute pi d squared over 4 in for the area, I've got a nice expression I can solve for the diameter. Okay, so what I did in this step was I just factored the d squared out, and then I've got all these other terms multiplying it. So since it's a bunch of variables divided by a constant, I'm just multiplying both sides by the constant and then dividing both sides by all those variables, and pi. Okay, so I've got d squared equals 4i over charge times charge density times drift velocity times pi. It's not the nicest looking expression, but it's okay. So I take the square root of both sides, and I have all my values. I plug them in. 5 amps, E, my charge density, and my drift speed. So once I calculate that, I get a very small diameter, right? 1.86 times 10 to the negative 2 meters. Again, makes sense. Most wires that we're talking about are fairly small in this case. So for the next part, I'm going to need the area, right? Maybe I don't recognize that now, but I calculated the area just in case, right? So I came back to my expression for the area here and substituted in for the diameter, and I got 2.72 times 10 to the negative 4 square meters. So the second part says we've got a 15 meter long piece of wire. What's the potential difference? Well, why do I need to calculate the area of the wire? Because I'm going to use Ohm's law. So I'm going to use delta V as I times R. I know the current, but I need the resistance. And they didn't give me the resistance in the problem, but they gave me the dimensions in the problem, and I looked up the resistivity of aluminum. If we were ever in a situation, where you had an exam or something like that, I'd be sure to give you the resistivity on the test so you wouldn't have to look it up. But I searched for the resistivity of aluminum, I found it, and I've got the dimensions, right? There's a 15 meter long piece of wire. I just calculated the area and I was given the current. Okay, so I looked that up on the internet. I calculated the area from the diameter I found in part A, and they gave me the length. So I substitute those values in. 5 amps, 2.82 times 10 to the negative 8 ohm meters for resistivity, 15 meter long wire, and the area I got in part A, and I've got a very, very small potential, 7.8 times 10 to the negative 3 volts. It takes a very small potential to drive a very high current through a conductor, right? That's why we use it. It doesn't take a whole lot of energy to run a high current through a wire, as long as it's a conductor. Okay. So this is a pretty interesting problem. I've got a block of copper. So it's a rectangular block of copper, so I can't change the shape of this block. So it's got sides 10 centimeters, 20 centimeters, and 40 centimeters. The block is connected to a 6-volt source across opposite faces of the rectangular block. Which faces? I don't know. It asks what's the maximum current that can be achieved and the minimum current that can be achieved. So here's what I did. I drew 3 pictures. Okay, I wrote my dimensions, right? I wrote the sides of my block, right? L1, L2, L3. All right, 1 centimeter, 2 centimeter, 4 centimeter. It's connected to a 6-volt power source, right, or potential source. So I don't know which sides, right? I don't know which side that this source is connected to the block of copper. So what I recognize is I'm asking for the maximum current and the minimum current. So if I go back to Ohm's law, current is inversely proportional to resistance, right? If I divided both sides by R, I would be delta V over R. So the higher the resistance of a material, the lower the current would be if I had a constant voltage, right? So they're inversely proportional. So what I did was I looked at all 3 scenarios. Okay, there are 3 possible scenarios where you could connect this block to a voltage source. And then I also said if there's a larger resistance, there's a smaller current, right? Smaller resistance, larger current. So basically what I'm looking for is how to connect the voltage source to this copper block to maximize the resistance and minimize the resistance. But I know also that resistance is resistivity times length divided by the area. Now I didn't look up the resistivity of copper just yet, but I do see that the resistance is proportional to the length of a wire, and it's inversely proportional to the area of the wire. So this is a ratio, right? This is a length to area ratio. I have the 3 dimensions of this block, so I can actually find all of these. So if I can find the length to area ratio for all 3 possibilities, I can see that the larger the L over A is, the larger this ratio is, the larger the resistance is, and then the smaller the current is. And vice versa, right? The smallest L over A ratio I get, the smallest resistance that this block is going to present. So I'm going to have the maximum current there. So basically what I'm going to do is I'm just going to calculate all 3 possible L over A's. Right? I've got 3 possibilities. I'm going to calculate L over A for each scenario, and then whichever L over A is smallest, that's the max current. Whichever L over A is largest, that's the min current. Okay, so first thing I'm going to do is I'm going to take this is the length, and then the product of L2 and L3 are the area. So what does that mean? Here's my block. It's standing up on that's centimeter, sorry, on the 1 centimeter by 2 centimeter side. Okay, so that means it's the 4 centimeter side is vertical. Alright, so I'm connecting the voltage source to the 4 and the 2 side, right? The 4 by 2 side, the large flat side right here. Okay, so that means the length of the wire, quote unquote, it's a block, but the length of the wire is 1 centimeter. The cross-sectional area is 2 centimeters by 4 centimeters. Okay, so that means the voltage source is going to be attached, right, to the largest ends, right, the 4 by 2 sides, and there's going to be a current running through it. So I get 1.25 1 over meters, right, or inverse meters, whatever you want to call it. I'm not really concerned about the units too much. Okay, but this is 1.25, so it's very small, right? But I want to try out the other scenarios. Now this is directly proportional to resistance. Okay, so this number tells me what the resistance is going to be of this block. So let's try the second scenario. I tried to draw them as best I could. So I'm keeping them, I'm drawing it the same way, right? I still got the flat side here, but instead of the current and the voltage source being on the flat side, or the large side, the 4 by 2, I'm going to make it go through the 1 by 4. You see this right here? I'm going to make it go through the 1 by 4. So that means the cross-sectional area is the 1 by 4, 1 centimeter by 4 centimeter, and then the length is 2 centimeters, right? So the current's going through that way. Right? Current's going through that way. Voltage source, right, is going to be connected to either side of the block on the 1 by 4 sides. Okay, and I get 5 inverse meters. So the third possibility is running the current vertically, okay, through the 1 by 2 side, right, the 1 by 2 side right here. So that means the cross-sectional area is 1 by 2, 1 centimeter by 2 centimeters. And the length of the block that the current is running through now is 4 centimeters. And so I get a very large length to area ratio, 20 inverse meters. Okay, so who's the smallest? Right, this is the smallest length to area ratio. That means it's got the smallest resistance. That means it's got the maximum current. Same thing with scenario 3. This is the largest length to area ratio. That means it's going to be the largest resistance, and it's going to be the minimum current. So I'm asked for the min current and the max current. So that means I know the voltage source. I'm going to use Ohm's law, I equals V over R. I don't know the resistance yet, but I know the length to area ratio, and I can look up the resistivity of copper. Here it is. So basically, if I go up here, right, I've got rho L over A for resistance. Okay, rho L over A for resistance, but now resistance is in the denominator, so it's going to be delta V over rho L over A. Okay, so A is going to be in the numerator, rho and L are going to be in the denominator. So I look up the resistivity, I factored this L over A, right? I grouped it together into its own term because we already calculated that. So delta V I know, rho I looked up, A over L is 1 over 1.25 inverse meters, right? So these inverse meters are going to come up here, they're going to cancel, I'm going to get volts over ohms, and I'm going to be in amps, and everything's going to be good. So I throw my voltage in there, my resistivity, and this length to area ratio in, and I get 2.82 times 10 to the 8 amps. Okay, very, very high current. So that's the max current that I can send through this copper block. Minimum current, same process, so it's same resistivity of copper, but my area over length ratio is 1 over 20 inverse meters. Okay, again, this is flipped, right, because I calculated L over A, and I get a minimum current of 1.6 times 10 to the 7 amps. Okay, so kind of a fun exercise there, some different possibilities, something kind of make you think there. So I have one more little topic at the end of chapter 17 that we'll talk about before wrapping up this chapter and moving on to chapter 18. Okay. Alright, so we're talking about capacitors and capacitance. Now, unfortunately, we're not in lecture, so normally I'd take an old one of these and I'd open it up for you. So what's actually in here is this is two flat pieces of a conductive material wrapped around tightly in a coil, and then there's a dielectric material in between it. It's kind of like an insulator, right? And you can unravel it, and it's really, really long. What we know so far when we hear the word capacitor is a parallel plate capacitor. And that's basically what's being recreated here. So it's two parallel plates, it's just wound by a coil, right? So if you ever see anything like this, I think we have pretty much, sound bars everywhere, but if you ever ran into like an old stereo receiver or something, you'd see a lot of capacitors in there. So that's a parallel plate capacitor, what we've been dealing with. So it stores energy in the form of an electric field, right? And what we can do is we can move the distance between the plates, right? We can change their capacitance. We can charge them, we can discharge them, right? We can store energy in them for later, so we can do work. So how do we charge a capacitor? Well, we have to charge a capacitor by connecting it to a potential source, something like a battery. Okay, so and what we'll see in one of our labs is that once you connect this battery to the capacitor, after a certain amount of time, the potential across this capacitor is going to be equal to the potential across the battery, right? So we've got the positive end of the battery is going to attract all the negative charges off of this plate, and then the negative end is going to push all the negative charges onto this plate, right? But eventually we're going to run out of negative charges to move, and then this potential difference across the capacitor is going to be equal to the potential difference across the battery. The expression, for the sake of avoiding rigorous derivations, the electric field in between the plates of a capacitor is the charge on the capacitor, the total charge on the capacitor, divided by epsilon naught times the cross-sectional area of the plates, right? The surface area, I should say, the surface area of the plates. Epsilon naught is this constant right here. That's the permittivity of free space. And think about permittivity of free space as the ability for an electric field to pass through free space or a vacuum. Okay, so this is the ability, right, of the electric field to pass through free space, right? So this would be different if you were trying to pass an electric field through a dielectric, or an insulator or water or something like that. But this is a constant value, right? Permittivity of free space. So it's directly proportional to the charge on the capacitor. Makes sense. But it's inversely proportional to the area. So the larger surface area you have on the plates, the weaker the E field is going to be, because the charge is going to be distributed across a larger area. So what is the capacitance? Right, the capacitance is the ability to store energy in a capacitor, and that is the charge divided by the voltage across the capacitor. Right, so it's the charge divided by the potential difference. Now what I did to get this other expression is, sorry, it's a little light here, okay? So I took C equals Q over V, right? So it's charge over voltage. I'm going to rewrite this, and I can solve this for Q, and I get Q is V times C. Q is V times C. But I want another expression for capacitance. So I'm going to write the potential difference as the electric field times the distance between the plates. If you go all the way back to, all the way back, a chapter ago, if you go back to chapter 16, we solved for the potential difference across a set of plates, and we used the distance between the plates times the electric field, and we got the potential difference. Now here I'm only concerned with the magnitude, right? So I don't really care about the direction of the electric field right now. So it's E times D, electric field times the distance between the plates. So if I substitute this in here for the potential difference, I have the electric field expression in the denominator. But the electric field is Q over epsilon naught times the area. And so I substitute that expression in for the electric field, Q over epsilon naught A. Okay, it's in the denominator, so it's flipped. The Q's cancel, and I'm left with epsilon naught times the surface area of the plates divided by the distance between the plates. And so that means that capacitance, I can create a capacitor with a cross-sectional area and a distance, and that controls the capacitance, right? Not necessarily the potential or the charge on it, but I can make a capacitor with a certain capacitance just by changing its dimensions, right? Changing the distance between the plates and the cross-sectional area. The SI unit of capacitance is the farad, named after Michael Faraday. We'll talk about him in chapter